Okay, I'm back. Hopefully you guys did okay with the problems about thin film interference, and I'm going to leave it as an exercise for you to read the section 27.4 about the Michelson interferometer, and we're going to move right on to section 27.5, which is about diffraction. So we talked about diffraction before with sound, about the reason why you can hear sound around the side of a doorway is because the sound waves bend and they spread out when they go through a doorway. And that happens with light also. However, the amount that the wave spreads out, the angle through which it spreads, depends on, whoops, let me go back. The angle through which it spreads depends on the wavelength of the light and the width of the slit. I keep doing that because I need to switch to my pen. Screen, pointer options, pen. There we go. Okay, let's try this again. So the wavelength divided by the width of the slit determines the angle that it will diffract. So if you have a smaller ratio or a larger ratio of wavelength to width, then you'll get a larger amount of bending. So in other words, if your wavelength and the width of your slit are on the same sort of scale, then you'll get an appreciable amount of bending. So for light passing through a doorway, wavelength is in the billionths of a meter, and the width of the slit is on the order of 1 meter. And so if you take, say, 450 billionths of a meter divided by 1 meter, you're going to get something very, very small, and therefore a very small amount of spreading, and you won't be able to tell. However, if the width of your doorway or slit is much, much smaller, then you'll get an amount of diffraction that you'll be able to see. So one way that we can look at why diffraction happens is based on Huygens' principle. So Huygens said that if you've got a wave coming in and hitting an opening, the reason why that wave spreads out is because you can think of each individual little point in that wave as its own new source of waves. And remember, a source of waves will produce waves that spread out in a spherical shape all around them. So if this wave produces spheres, and this wave here produces spheres around it, and so on, then you get all these spherical waveforms spreading out, and then that's going to cause a pattern of spreading like this. And you're going to get like a cone-shaped spreading of the wave. And these are called wavelets, Huygens wavelets. Alright, now moving on to the other picture. Okay, so now this picture is illustrating how for a smaller value of lambda over W, that would be the wavelength divided by the width of the slit, you get less diffraction. So here, the wavelength is shown here. You can see this is, I think, water waves in a tank that are all coming, being produced with the same frequency, so they all have the same wavelength. So here would be sort of the crest of one wave and the crest of another wave. So you can see how this width is much larger than the wavelength itself, and so we don't get much diffraction. But here, our wavelength would be from here to here, from one crest to the next crest, and now our slit is about the same size as our wavelength, and we get much more obvious diffraction. Here's another example. If we shone light through a slit and we didn't see diffraction, we would just see that shape on the screen on the other side. And that's pretty much what we see for a slit that is, you know, on a larger scale. But if we have a slit that's a fraction of a millimeter, then we see that the light spreads and we get this pattern. And not only do we get the light spreading, but we also get a pattern of constructive and destructive interference. And so on the next slide we're going to look at why that pattern occurs. So here, this is showing a top view of what we just saw on the previous screen. So our light source is somewhere over here, and it's shining the light this way. Those were supposed to be straight, but you get the idea. And then when the light hits the slit here, each one of these points acts as its own individual source. So if this screen is very, very far from the slit, then these are approximately parallel to each other. And so then they're all going to be traveling the same length to get over here to the screen. And so what we get over here on the screen is a bright spot, because these will all interfere constructively if they're all traveling approximately the same distance to get to the screen. So we would expect to see a bright spot in the middle of the screen. If we drew a line from the middle of the slit over to the screen, we would expect to see a bright spot on the other side. And that is what we see. And if we go back to that picture, that's what's showing up right here. However, if we look at another spot a little further down, now if we assume these are all parallel again, because the screen is much, much farther away than the size of this slit, then these are not all traveling the same distance to get here. And so we get a dark fringe here in exactly the opposite situation of where we got a dark fringe for two-slit interference. So remember, for two-slit interference, when we had the light coming from one slit and another slit off by exactly one wavelength, we got a bright spot. Well, now if we look at, say, 3 of these wavelengths, or 3 of these little point sources here, what we see is that we get our first dark fringe when this bottom one is exactly 1 wavelength longer than the top one. And so at first that seems like, well, why don't those create constructive interference? But you have to remember, this one and this one aren't the only sources of the light. It's not like two-slit interference where there's just this source and this source. There's also all the ones in between. And so if we look halfway down, we'll find a wavelet whose distance traveled is exactly half a wavelength. And so this one's going to interfere destructively with this one. And if we look at a point just below number 1, and we look at a wave just below wave number 3, those two will interfere destructively as well. And so on. If we look at a point just below there and a point just below here, those two will interfere destructively. And so when you have this N1 with a wavelength, or where this is exactly 1 wavelength longer than the one at the top, then for every wave in the top half of the slit, you get a wave in the bottom half of the slit that's canceling it out. And so that produces a dark fringe. So the equation that we can use to figure out this angle here is the same equation that we used before for two-slit interference. D sine theta equals m times the wavelength. Now D here indicates not the distance between the slits, but now the width of the slit. Our angle theta here is the angle between the line that goes from the center of the slit straight across to the screen and a line that goes from the same point to the first dark fringe. M, of course, is an integer again, and then lambda is still the wavelength of the light. Okay, so the difference here is that this angle here, this is where we get our first dark fringe, not where we get our first bright fringe, or our second bright fringe, as it would be with two-slit interference. So if this distance here, we'll call this L again, just like we did before. So we'll call this distance L, the distance from the slit to the screen. If that is much, much larger than this distance, this was what we called XM before, then we can say the hypotenuse here is approximately the same thing as this L. So that happens if this XM, or the distance between the center and the first dark fringe, is much smaller than the distance from the slit to the screen. And if that's true, then sine theta, which is normally written as sine theta is opposite over hypotenuse, we can say that's approximately equal to opposite over L, if the hypotenuse is approximately equal to L. So again, if this side of the triangle is very small compared to these other sides. And so that would be opposite over adjacent to our angle. That's our tangent. Our opposite side here, remember, we're calling that xm. So xm over L is approximately equal to sine theta. So we can plug that in for sine theta, and we get the same thing that we had before. We have d times, instead of sine theta, xm over L is approximately equal to m times lambda. And if we rearrange that, xm is approximately equal to m times lambda times L over d. Now the difference in using this equation for one slit interference is that this is the distance to the first dark fringe from the center. From center to first dark fringe. This is not writing very well again. Dark fringe. And then d, of course, wouldn't be the distance between the two slits because we only have one slit. D is then the width of the slit. Okay, we're going to pause. We're going to stop here, and then in the next video we're going to look at an example.